So in the previous sessions we have started doing some problems based on change in entropy involved in various thermodynamic processes. So far we have done three sample problems, starting with two cases that we have already discussed. One was related to the change in entropy during some isothermal process undergone by ideal gas system. And then we have done two problems on the heat exchange happening between two thermal energy reservoirs. Okay, now we will take our discussion to further problems in which there are some phase changes happening for the system. So let's start with this particular problem and how to tackle the problem. So problem number 4 for us is calculate the change in entropy when 10 gram of ice at 0 degrees Celsius is converted into water at the same temperature. And you are given latent heat of fusion of ice equal to 80 calories per gram. See, on the side I have given some more data. Okay, this data I will discuss at the end. These data are not used for the present problem, so only one of the data is used for the present problem, but I suggest you strongly that you remember these minimum these three data whenever you are trying to solve a problem in entropy change. These three data will be useful even if the data is not provided along with the problem, as it happens usually. You should be able to recall it from your memory. So this is what I suggest. Okay, these values we already have discussed in our previous module, but let me remind you that these data are important to be memorized. So let's see how to do the problem. So you can see that here you have got some amount of some mass of ice. So the process here is, let's discuss the solution. The process here is you have got ice. Okay, ice at 0 degree Celsius. So ice at 0 degree Celsius. You know that in all these thermodynamic problems we prefer to convert into the corresponding Kelvin scale. See that you do not forget about that one. So let me say that at 273 Kelvin. So see that you do this conversion then and there. Do not forget. Okay, so ice at 0 degree Celsius has to be converted into water at the same temperature. So we can see that it's just converted into water. So let's analyze the problem first. That is always a part of solution. So water at the same temperature. So it's given that at 0 degree Celsius. So this is the situation. Means it's there is no temperature change involved in the problem. Okay, and clearly you know that this is nothing but a phase transition from solid to liquid, and this is an example of first order phase transition. As we have seen, every first order phase transition involves some sort of heat. Okay, that is known as the latent heat, right? And the latent heat here is conversion for ice to water, that is the latent heat of fusion of ice, and whose value has been provided along with the problem, right? Now also we have discussed in our theory part that for what purpose this latent heat is being used up, because it even though heat is absorbed, you can see that there is no any visible change in the temperature of the system. So where actually this heat is being used for? The answer also we have analyzed and found that this heat is used for increasing the entropy of the system, or it is used to increase the molecular disorder of the system, without increasing what you call the temperature of the system. Okay, so that is the answer. So we are supposed to find out the entropy change here, right? Now hope you remember from our discussion of the strategy of solving such problems. So in phase change problems you have to use the same equation. So our basic equation in any process which we are assuming to be reversible, we assume that all these processes are reversible, and then we are using the equation ds is equal to elemental change or infinitesimal change is equal to simply dq by t. ds equal to dq by t. Or since this is a finite change, finite change, I can consider this one as a finite change. I can replace ds by delta s. There is no issues regarding whatever symbol you are using. So instead of dq, let me just write as some delta q. Okay, it's only for our purpose of converting. Okay, delta q by t. So now the question is that temperature has been given, because temperature during the process, temperature remains constant. So you are given the temperature is equal to 273 Kelvin. So there is no confusion regarding it, which temperature to be used, right? Now the question is that how do we get this delta Q? How do you get this delta Q? And in order to get this delta Q is the amount of heat that has been absorbed by the system for the phase transition. And you know this delta Q is nothing but can be expressed in terms of the latent heat of fusion of ice. So that is equal to M into LF. Okay, because LF is equal to delta Q, heat required per unit mass for the phase change to occur. So delta Q equal to M into LF. So I can write this one then and there as what? M mass of the sample into the latent heat of fusion. In this case, it's a latent heat of fusion. Okay, so by T. So that is the equation. So now it's a matter of just substituting with the proper units. So it's equal to what is the mass of the sample given? So here it is given as mass is 10 gram of ice. So mass is equal to 10 gram. So you can just always write down all these all these values beforehand, and if needed you can convert. And 10 gram of ice, you know, it's not an SI unit, but let's have a look at what is the unit in which latent heat is given. You can see the latent heat is also given in calories per gram. Per gram it is given. So you need not take the pain of converting to kilogram or in joules and all if it is not asked for you. Okay, or if it is not in a competitive examination where you are given the question units are in grams and the answers, the choices are multiple choices are finally given expressed in some other unit, then you need to convert it always. Okay, but it's a mix of units that we will be using mix of units also, but every time you be careful that you are using the temperature always in Kelvin. Okay, temperature should better not to use in degrees Celsius. Okay, temperature let it be expressed in Kelvin. Okay, other one it's we are just leaving it as an option for you, depending on the requirement or depending on the other values. See that you just either use the same unit calories per gram or you convert it into joule per Kelvin, whatever it is. Okay, sorry, joule per kilogram. Right. So anyway, since mass is in gram and LF is in calories per gram, let me use the same unit. So that is 80 calories per gram. 80 calories per gram. So can you just directly substitute it and get the answer? So it's equal to simply mass is 80. So it's 80. Sorry, yeah, mass is 10. Sorry, mass is 10 grams into what is that? LF. LF is 80 calories per gram. So automatically the final answer will be in calories there, right? So 80. 10 into 80 divided by temperature is 273. So temperature is 273. You can just multiply. This is equal to some 800 by 273. Okay, so it will be pretty something close to 3, right? Okay, so the unit will be equal to, so it's when you calculate this value, you'll be getting it's around 2.93. That's a numerical value. 2.93. What will be the unit? Because I used calorie, is it not? Calorie. Joule per Kelvin is the SI unit of change in entropy or entropy, but it's what? Calorie per Kelvin. So the unit will be here, calorie per Kelvin. So this is the answer. It's quite straightforward a problem, only to make you clear about different varieties of problems that you may come across. We have discussed it. Now, before we move on to the next problem, please look at this standard data that will be useful for you. So one is that what we have already used. Always remember or memorize this fact. Latent heat of fusion of ice is I represent as LF. For F stands for fusion. That is 80 calories per gram. Okay. You can have its equivalent value in joule per kilogram also, no problem, because you always know that 1 calorie is equal to 4.18 joules. So whenever you need it, you can convert it. Or so roughly it's equal to 4.2 joules. 4.2 joules, right? So since 80 is memorable, easily memorable value, I prefer to use this value, but depends. Right, now another one is that there may be questions involving vaporization of water, like instead of ice to water, what is the next stage that is possible? Water can be certain amount of water at 100 degrees Celsius can be converted into steam at 100 degrees Celsius, right? So there will be of course what is known as the latent heat of vaporization will be involved. Okay, so we'll do such problems also later in the coming sessions. So in that case, you need to remember what is the latent heat of vaporization of water, or latent heat of steam, you can say latent heat of steam. So that will be equal to 540 calories per gram. So that is the thing. The second data. Now there will be problems involving water at say 0 degree Celsius heated to some water at some other degree Celsius, say 100 degree Celsius. So there is no phase change. Okay, it is liquid water itself, but you need to use what is known as specific capacity of water, and whose value you pretty know. Okay, so in calories per gram, it is 1 calorie per gram per Kelvin. Okay, 1 calorie per gram per Kelvin. Now in terms of joules, it will be 1 calorie is 4.18 or 4.2 joule per gram per Kelvin. If mass of water is given in kilogram, then it becomes, you just multiply with what, 10⁻³ that's all. Okay, it will be 4180, or roughly this is equal to 4200. Okay, since you are using calculators, it's better to be precise. So 4200 joule per kilogram per Kelvin. So these three data are very important as far as change in entropy problems are to be faced. Okay, be careful about it. Hope it is okay with you. Now let me go to the next problem. Let's say problem 5. 1 kilogram of water is heated from 0 degree Celsius to 100 degree Celsius. Be careful about when you read the problem. Try to identify which category it belongs to. Calculate the change in entropy of water. So that is the 1 kilogram of water is not 1 kilogram of water is converted into 100 degrees Celsius of water. Okay, so there is no any phase change involved. That is the first thing you have to identify. So I can say that given, right? We can take given or the data. Okay, mass is equal to 1 kilogram. So writing down all these values will give you some idea. Mass is there. Then water is heated from 0 degrees Celsius to the other one. So what is that? T1. So I can say T initial or T1. T1 equal to 0 degrees Celsius. And I prefer to convert it into what? 273 Kelvin. Okay, and what is the final temperature of water? That is T2. T2 is equal to 100 degrees Celsius. 100 degrees Celsius is none other than 373 Kelvin. All right. So this is just a case that we have discussed. How do we do that? Okay, hope you remember that our equation was some ds is equal to, always ds is equal to what? See, dq by t. ds is equal to dq by t. So what will be the this is for infinitesimal process, so what will be in this case? So delta s will be equal to, right, delta s will be, here is there is a change in temperature, so delta s is equal to integral from, right, initial temperature to T1 to T2. Okay, so dq by t is not dq by t, dq by t. And how do we convert T1 and T2 are given, it doesn't matter. Hope you remember this equation. So dq can be written as what? Something like mc is not, dq is equal to mc dt. That was the equation that we had done. We have discussed this one previously. So this is nothing but equal to T1 to T2. Directly you can recall this equation and write it. mc, okay, mc dt, c is the specific capacity of water, mc dt upon t. And you know what is the resulting equation? We derived it. So it is treating the heat capacity of water to be remaining constant for the range of T1 to T2. We can take it outside and it will be finally giving you mc log of T2 by, is not, okay, T2 by T1, mc log T2 by T1. So this will be the equation that will be useful for us. Now can you see that every data is available with us? Okay, of course, m is given, c is given, T2 and T1 are given. So see that you substitute in proper units. So this is the equation that will be handy for us in such problems. Okay, so delta S. So let's substitute it. It's equal to, what is the mass? Mass is 1 kilogram. So that's 1 kilogram. All right. So we need to have one more data here, right? Yeah, 1 kilogram. Let me go on writing the units also. It will be also helping us if needed. Okay, then C. What is C? Since it is in kilogram, I have to use the C of water, that is 4180, okay, 4180 joule per, right, joule per kilogram per Kelvin, right, joule per kilogram per Kelvin. So that will be the better unit. So I can write that is 4180 or 4.18 into 10 raised to 3, whatever it is, 4180 joule per kilogram per Kelvin, okay, into natural logarithm of, okay, T2 by T1. So what is T2? T2 is 373. So it will be 373 divided by, okay, 273. Kelvin will be getting cancelled, okay, when you take the ratio, that's all. Alright, so that will be the thing. So just what will happen here, let me just, so here it is kilogram and here it is what, kilogram per Kelvin, right? Sorry, kilogram inverse. So they will get cancelled. So whatever it is, it will be equal to, just you have to multiply this, take a logarithm of 273 by 3 here, 373 by 273, and you just multiply it. If you want, you can just convert into 2.303 and take convert into logarithm 10. Doesn't matter, you are permitted to use calculators, so you can just work it out directly, and you will get this answer roughly as some 1300. Okay, 1305. Just check it. I'm taking this value from some standard textbooks. That's all. What will be the unit? You can see that it will be joule per Kelvin, right? What remains is joule per Kelvin. So this is a way in which you get proper units, joule per Kelvin, and that's a SI unit of change in entropy. Okay, so this is our answer. So joule per Kelvin. Now it's a straightforward equation. Okay, like problem. Now before we proceed on to the next problem, just have a logical checking of the answer that we are right at. See what we are discussing. We are discussing water at 0 degrees Celsius getting converted to water at 100 degrees Celsius. So we can see that the delta S is positive. Delta S we are getting as positive. Okay, why delta S is positive? Because heat has been absorbed. There is a heat transfer to the system. So heat has entered the system. Hope you remember that when heat is entering the system, automatically, neglecting all other factors, you can suppose that the entropy of the system can increase. Remember, entropy of the system can increase. Okay, so you can automatically, just check it, or you can think on it. If the problem was the reverse, if the problem was given as the reverse, what is that? 1 kilogram of water at 100 degrees Celsius cools down to 0 degrees Celsius. What will be the change in entropy of water? So you can understand that in that case, what happens will be this T1 and T2 will get interchanged. What will it be? T1 and T2 will get interchanged. So when T1 and T2 will get interchanged, so it's actually MC log, the actual equation is MC log T final divided by T initial. Okay, this is the real equation to be remembered, no? MC log T initial to T final. So it should be MC log T final by T initial. So in cooling problem, what will happen is that it will be MC log, okay, in such problem, T final. T final will be 0 degrees Celsius. So it will be 273 in this problem I have discussed. Divided by 373 it will come. So what about this number? Log of a number less than 1. Log of a number less than 1 is what? Negative. So you will get, in this case, delta S will be obtained as negative. So you can interpret this result also. Why this delta S becomes negative? Because heat has, okay, just what? Flown. Okay, heat has got rejected out of the particular system. Out of the system. We are talking about the system. What happens to the entropy of the system, right? So you always check your answer, whether your answer of the numerical problem is as you expect. Okay, that will be helping you in just checking the logical correctness of the problem. Okay, fine. So let's do one more problem in the session, and then we will just So let me go to the next problem. So this is our 6th problem. See, always on verifying that what we are doing, I'm trying to give you a systematic understanding of how to do problems step by step. Okay, that's my purpose. Now let's check it. Calculate the change in entropy when 1 gram of water at 100 degrees Celsius is converted into steam. 1 gram of water at 100 degrees Celsius is converted into steam, right? So this is the third stage, right? We started from ice to water, then like water from one temperature to another temperature, Now it is what? Water at 100 degrees Celsius to converted to steam. So you can see here it is water at 100 degrees Celsius. Let me write it as what? 373 Kelvin. This is my system. It's getting converted into steam. Yes, it is given that it's steam, means you can take, if since the temperature of steam is not given, you can take that steam at 373 Kelvin. That's what they mean in the problem, if it is not otherwise specified. Steam can be at a higher temperature, of course, okay? So but it is steam at 373 Kelvin. That's what they mean in the problem. So of course you can see this is a phase change, phase transition. So in phase transition, you know which quantity will assume importance, that is the latent heat will play the role. So during this process, which one? Latent heat of steam or latent heat of vaporization of water, that will come into effect. So here you can see that dq will be equal to simply m into L of vapor. Okay, so dq will be for this much amount, m into LV, right? So you can do it in the same manner. What is there? You can say, yeah, here see that in this problem what is not given in the problem. It is latent heat of vaporization is not given. No any hint is given. So in this case, in such cases, you have to recall from your memory. Okay, what is the latent heat of vaporization of steam? That was 540. That's what I told you. Okay, or we have been using calories per gram. Calories per gram. Okay, so let me do it here. The problem. That is the mass given here is how much? 1 gram, right? 1 gram. Temperature here is 373 Kelvin, that is constant. And see, latent heat of vaporization, what we know is in calories per gram. Okay, so I think you can retain the problem in calories per calorie itself, right? Okay, so what we can do is that temperature is in Kelvin, make sure that right. So delta S. So as usual, we are done earlier. Delta S will be equal to delta Q over T, and delta Q will be equal to earlier it was m into LF, now it is m into LV divided by the temperature. So can you just substitute it? So that is equal to 1 gram. So there is no problem. 1 gram into latent heat of vaporization is what? 540 calories per gram. Okay, I am substituting the units also along with, so that you are familiar with how our final answer will turn out. So divided by 373 Kelvin, right? So what will happen? This gram and gram inverse, they will get cancelled finally, and you will be getting 540 divided by 373. 373. What will be the unit of this entropy change? It will be calories per Kelvin. Okay, calories per Kelvin. So that is equal to, it's roughly, you can see that's roughly 2, so it will be equal to 1.98. if it were just other one, so 1.98, that's a thing. Okay, just check the values. Just okay, it's a value that is given here. Even otherwise also just check it. Okay, so it should be lesser of what I feel. Okay, doesn't matter, just check it, check this particular value, right? So that is about it should be lesser than this one, because if it is 270, it should have been 540, like, so it will be 2 in that case. Okay, yeah, just now so that's about the third kind of problem. Okay, so practice more problems of this kind. We will take up some more problems in the next session. Okay, thank you.